In this video, we're going to talk briefly about Ohm's law. So what we've discussed so far, we've covered a lot of things about resistance, current, power, and potential difference. We have many of their rules and definitions, units, etc. We even have an equation that relates power, current, and voltage together, the PIV equation. The one thing we don't have is we don't have the definition for resistance and or an equation that relates these three things together. And that's what we're going to get with Ohm's law. So to start thinking about this, we can ask ourselves, what are two ways to decrease the total current through a circuit? So if we have something like this where it's a circuit, a battery, and a light bulb, we could do two things. One, we can get a smaller battery, so like decrease the potential difference, so something with less voltage, right? And then all of a sudden there'll be less push around the circuit and there'll be less flow. The other thing we can do is we can get a less conductive material, something that conducts poorly, or in other words, we're basically bumping up the resistance in the circuit. So it could be from the light bulb or the wires, or something that increases the total resistance in the circuit itself. Okay, so this brings us to what we call Ohm's law. When you have something where you have a circuit like a light bulb, and if you keep, with a battery and a light bulb, and you keep that temperature of that circuit relatively constant, then hopefully one thing should happen, and that is that the current will stay proportional to the voltage. So like if we had before, like that circuit, if we kept bumping up the voltage of that battery, kept on making it bigger and bigger, the current should get bigger, but it'll also get bigger in a proportional way. This is true for a lot of resistors as long as the temperature is constant. This is known as Ohm's law. So we can have things that, or resistors that follow Ohm's law, and we can have resistors that don't follow Ohm's law. So this law is not like irrevocably decreed and is always true. This is just like, hey, this is great when this happens. So here we have two examples, one graph that follows Ohm's law and the other one that does not. Here the current is proportional to the potential difference, and here it is clearly not proportional because it's not straight. Nichrome wire is a great resistor that follows Ohm's law, and we say it's an ohmic resistor. Light bulbs are terrible ohmic resistors. They do not follow Ohm's law. As the voltage gets bigger and bigger and bigger, what ends up happening is that the resistance starts increasing as well, and so this graph begins to curve. So if it's proportional, that means the current is equal to some number times potential difference. That some number K turns out to be the inverse of your resistance. Because if you're getting, like if that graph is steeper, right, you're going to get more and more current for the same potential, and so you're less resistant, or vice versa. As if it's more shallow, it takes more and more potential difference for not very much current, therefore it's more resistive. So on the IB test, they like to write the equation like this: I equals delta V over R, which is nice because it kind of shows the two things that affect current. The more voltage you have, the more current you have, because these are proportional. And well, in an ideal world where it's ohmic, right? And then if you have more resistance, then current goes down because these are inversely proportional. And this is a nice relationship to remember, and this relates our three variables, potential difference, current, and resistance together. However, there are some things that you should know. This equation really brings us down to the fact that of what resistance is. We've never really defined resistance, although we've been using it this whole time. A resistor we often think of as something that just resists the flow of charges, and that's all we've thought of it as. But technically it's defined as this equation right here, which is stated as the resistance is measured by the potential difference required per unit of charge. And so if we just rearrange that equation we saw before for resistance, that is our very definition of what we define as resistance. Something is more resistant, right, if it takes more potential difference for the same amount of charge as another one, where these are the variables and the units. So coming back to this, one thing that is really important to keep in mind is that the resistance is not actually related to the slope. Because of this equation, we often think about this and we say, the steeper the slope, therefore the greater the smaller the resistance, because it's proportional to the inverse, right? And we think, oh, okay, that makes sense, but it's actually not the slope at all. The slope of this graph would be the change in current and the change of potential, or electric potential. Sorry, the change of delta V, right? So this is the slope, and this is not true. I need a little slash right there. This is not true. doesn't work. That's not what resistance is. This is resistance, right? Resistance, if you want to find resistance, you're going to take a point on the graph, right? And then if you want to know the resistance for this voltage, you would come down here and you'd take this potential difference number, you'd plug it in, you'd take this current number and you'd plug it in, and you would solve for R. So that's fine and dandy for ohmic resistor. What's so great is that no matter where you are in the graph, this number and this number, you divide those and you get the same number no matter where you are because they're proportional. And that's why we like ohmic resistors. A non-ohmic resistor, though, if you take this value right here and you divide it by this value, you get some resistant number, but that's very different than if you take a value over here and over here. And so therefore the resistance is changing. Just please don't think that to find the resistance, you're going to have to like calculate the slope of the tangent line like we've done in past things. That's not what you have to do. You just take the values and divide them. So we can practice one right here. So this is a question from an IB test question, and it's just simply what is the resistance? And you're supposed to solve. Note, this graph is backwards from what we normally do, right? Here's voltage, here's current. Usually we have voltage down here and current up here, but they can switch it on you on the test, so be careful to read it accurately. So it should be delta V, which is 2, and we want to find the resistance when the potential difference is 2. So we're going to take 2, and then we're going to just simply divide it by 1.2, and that will be our resistance. All right, so now with this final bit of information, we now have, our knowledge of Ohm's law, we can rearrange it into the form of this, which is how they write on the IB or AP test, and relates current, resistance, and potential difference together. And now we technically have the equation or definition for resistance, which is potential difference per unit charge or per unit current. All right, let's see it in action. All right, so if we had a question like this where we have 3 resistors all in series, and there's a battery here, 18 volts, and we want to know several things. We want to know what is the total resistance, what's the current through the battery, the current through 1, 2, and 3. I'm just going to call this resistor 1, 2, and 3, for lack of a better word. And what's the potential difference across all 3, okay? And these are the questions that we want. So in order to solve for this, we're going to use the rules that we have and also this newfound equation that relates IV and R together. So to start off, we're going to find the total resistance. These are all in series, and so we're going to use our rule for series. We're just going to add it all up, and we find a total resistance of 92 ohms. Second, it said, hey, what is the total current going through the battery, right? That was one of the questions. Well, we know the total resistance, the resistance of the entire circuit. We know the voltage of the entire circuit comes from the battery is 18. And so we can find the current of the total. So we're going to use our equation that relates these together. Oh, sorry, I forgot. I'm going to try and do something else. I could try and find the voltage across. I didn't know what order my prayer point went in, apparently. I'm going to try and find the voltage across this first one. And I'm going to say, okay, what's the voltage across this one? And I can use that equation, I equals V over R, but rearrange it. Notice I'm dropping the delta V's because I'm lazy. I'm just writing V. And I want to solve for this, but I know the resistance, but I don't know the current. I don't know the voltage. So if I can try and use this equation in certain circumstances if I don't have enough information, then go find something else. So I'm going to come back and find the current like I said earlier. All right, so here's the advantage to using this equation. I can use this equation for the whole circuit. So in other words, I could find the total current, which is the current through the battery of the whole circuit, equals the total voltage of the whole circuit, which is 18 volts, voltage of the battery, divided by the total resistance of the whole circuit, which we now know is 92, right? So I'm looking for this. I don't know this, but I do know the voltage and resistance. And so I can use this equation and find the total current going through here is 0.2 amps. Now, how does that help me? Earlier, I wanted to find the voltage across this first guy, right? But I couldn't because even though I had the resistance, I didn't have the current. Well, now I have the total current, that is the current through the battery, right? Well, I know from my rules of current, right, that when elements are in series, the total current coming in is going to be equal to the current that goes through each thing. So if there's 0.2 amps going through the battery, there must be 0.2 amps going through all of them. So that actually tells me the current through resistor 1, 2, and 3. And now what I'm going to do is I'm going to use this same equation over here, right? And we're going to use it again and again and again. And this is the trick to using this equation, is that you can use it, I equals V over R, in terms of the whole circuit. So total I equals total V over total R, or you can do it for an individual element. You can do just the voltage just across the first guy, so V1, or I1 equals V1 over R1. And here we're just rearranging this equation to be in the terms of V, which is what I'm solving for. So now that I know the current, I can plug it in, 0.2 times its resistance, and find the voltage just across him. I can keep on going and find the voltage across each element. And there now we have the answers to each of our questions.